But what this is it's a LED light connected to a wireless sensor node, and then this metal part in the back is actually just a heat sink. So the idea is that we can control in software wirelessly exactly what frequencies of light this little guy is transmitting. Then we built a experimental setup where we basically took the light, we put it on a tripod, we pointed it at a background where we could either have a white image or show different types of images. We had an iPad, this is our mobile device set up there. We had a light sensor, and then to control the intensity of the light, we actually use an aperture, since we don't want to use PWMing to control the lighting intensity. And so what we saw was, okay, if you take a 1 kilohertz LED, and again, I apologize that you can't really see the depth in the image, but this basically has striped bars on it. If you look at the frequency domain of the image, since because of the rolling shutter effect, the bars are always perfectly horizontal, you basically only need to take the central stripe of your 2D FFT. So if you plot that, what you see, of course, is a big peak around 1 kilohertz, because we're broadcasting a 1 kilohertz sine wave. So we said, okay, well, what about 2 kilohertz? At 2 kilohertz, you see that the peak shifts. Okay, that's good. That basically means that we now have some ability to transmit frequencies. If you, for example, mix 2 kilohertz and 3 kilohertz, you'll actually get 2 different peaks. And so what we see is that this acts like a standard sort of frequency modulated communication channel. And so if you plot the signal to noise ratio across the different LED frequencies, you see a curve that looks kind of like this. So we know one side of this is limited by what people will detect as flicker, and then we start to see some attenuation pretty harshly at above around 7 kilohertz. And this data was taken on iOS type devices, which we think are pretty representative. So what that means is that we have a bunch of bandwidth there, which we can now modulate frequencies over. And there's some details in how we do that are kind of beyond the scope of the talk. But to give an example, here's kind of a binary frequency shift keyed signal being sent from it. So what you can see is any places where this particular frequency we're looking for is high, you can detect it as a 1. Any place where it's low, you can detect it as a 0. And what we're not showing here, the reason why it's 2 frequencies and not on-off shift keying, is you can't really shut an LED off, right? So you have to default over to a high frequency that's kind of out of the bandwidth range that you would treat as an off signal. So this is what it would look like with great SNR. It turns out if you have a lot of noise from image artifacts in the background, your performance drops off, but here, it's still actually able to demodulate the data bits. So we have this capability where we can essentially do frequency shift keying. We have this wide frequency band, and so we started to essentially look at, okay, well, what does this VLC channel look like in terms of more common communication parameters? And so we have a mapping on the right of how bright the light is versus how much SNR you actually get from the signal. On this side, we have kind of a mapping of bit error rate to the signal to noise ratio. And I guess the takeaway point from this is not so much the details of the slide, but in our current system, we're able to send 1.3 bytes per second, and we can operate over 26 channels. So that means you could have 26 different lights in a single room, all of which you were able to essentially demodulate simultaneously. And because phones are so fast these days, they can actually do that matched filtering in parallel in close to real time.
Now, think about building a dedicated network or communication for something like the smart grid. It's not viable. It costs too much money, right? Think about building a in-building network just to control the building. No, we're just going to use Wi-Fi. We're just going to use the existing infrastructure. We're just going to use a network for different purposes, right? Therefore, the separation of concerns does not apply anymore. We have to do co-design, right? And that's, I think, at the heart of cyber physical systems. We have to do model joint modeling of these environments and analysis of them. It's a major challenge, which I think will take years and years. But I think it has been acknowledged, the necessity of it has been acknowledged. From the security standpoint, today I want to talk about security. Why would people care about messing around with this type of systems? You might want to disrupt operations, cause blackouts, for instance, which we have not seen yet. We have seen Stuxnet, which was really a very good example of an attack of a cyber-physical system. It was an attack on the IT system, then destroyed a physical system, the centrifuges in the Iranian nuclear plants. You might want to, so cyber warfare is a big, big reason for attacking a cyber-physical system. And in the commercial arena, think about your competitors being, so what you want to do is be more productive, more efficient than your competitor. So maybe you want to send a stealthy attack so that you don't get detected, but it reduces enough the productivity of your competitor so that you become more competitive, you can drive them off the market, for instance. And you can start rigging markets. Right? For instance, the electricity market is driven by the estimation of the power flow on the network. Right? If a line is congested, the cost of electricity is higher. Right? If you can change some of the measurements there, then you can make certain lines look more congested than others, and therefore you can drive prices. So then if you hedge your bets against them, then you will make money. Just some examples to keep in mind. So the natural question here is, okay, so we have lots of methods in cybersecurity that will deal with it. Problem solved. Well, I think there are some subtle, not so subtle differences between cybersecurity and what we would call cyber physical security. Okay, so cybersecurity deals with confidentiality, integrity, and availability, mostly of information. Right? When in CPS, we really care about the guaranteeing reliable system operations. So security here is more related to reliability, right? And of course, cybersecurity is a tool toward that, but I don't think it's a comprehensive tool.
So again, just based on surface characteristics, you can probably guess a lot about the relationships already. And also, if you look at the SMS log, you can see that I have several SMSs with these two people, and it's also spread out over several years too. Right? So that also tells you a lot about the relationships. And here's sort of a visualization of my call log data as well as some of the SMS log data too. So here you can see, at the top it shows call logs, the call log from my wife, and you can see that she calls me on all days of the week and all hours of the day. This over here is the length of time, so you can see that we have a few long calls and a lot of short calls. Now, just sort of a quick aside here, I actually did show this data to my wife, which was probably a mistake, because the first thing she said is, I don't call you that much. And it's like, but the data's right here. So the lesson to learn here is don't use empirical data with significant others, because that won't work. You can also see that my brother's over there too. Again, same kind of pattern. Calls all days of the week, all hours of the day, lots of different phone calls. But in contrast, if you look at my best friend, you can see we actually we don't actually talk that much. But when we do talk, we actually have very long phone calls. And you can also see, again, over at the far right, this one unknown contact only called once. Yes?
Did you track like incoming versus outgoing to see, how often the people call or how often you call?
Yeah, so the question is, do we track incoming, outgoing? Yeah, we actually do have that. We have probably about 100 plus features and includes things like that, length of calls and so on. So pretty much any feature that we can imagine we had inside of there. And sort of the upshot here is just examples of using this kind of data like that. Just using GPS co-location data, we found out that we can infer with 92% accuracy, are you likely to be friends with this person or not? Just if all we had is co-location data, or just GPS data from a lot of people. And using the call log data, contact list, and SMS log data, we can infer whether someone's family, social, or work with 90% accuracy. And the tie strength, is it someone who's close to you or not, with roughly about 75% accuracy. Okay? Now this is just one example of inference. Let me tell you about another kind of inference. Can we infer if someone is sleeping or not, just based off of their smartphone sensor data? And so here is, this is motion data, and here's ground truth data, sort of the highlighted area here. And so just based on this data, you can sort of see where this person went to sleep and where this person woke up. And this is using sound level data, and you can sort of infer the same thing too. Right? And in case you're wondering why we're looking at this is sort of like stepping back. The reason why we're looking at data like this is we're trying to see, can we use smartphones to infer depression inside of people? So looking at their social relationships and the change over time, sleep patterns, physical activities, cognitive behaviors, and so on. Right? So this is still work in progress, but I want to try to convey to you, this is an example of the flavor of kinds of things that people can infer about you using these kinds of applications.
We also had some what we call composite attractors, where we combined some of these things. So we had the animated connector that animated in and then paused before you could actually install. We also had one that had both the animated connector and the swipe, and then we had the animated connector and the reveal. So those three combinations. All right, so this was our whole list of different conditions that we ran, and to help you keep track of them all. So the two on the top do not have anything to attract your attention to the publisher. So the short options and no AV. The rest of them are all what we call attractors. They all attract your attention to the publisher. Now of those, all except the ANSI one are what we call peril sensitive, in that they attract your attention after you've tried to click the install button. If you just go ahead and click the don't install button, then it doesn't do any of that animation. It just lets you through. But if you try to click install, then they do something different. And so peril sensitive. Now some of them are also obstructive. So it turns out the animated connector one, you can actually go ahead and install while it's still animating. The rest of them, we actually locked it down. So until it had finished doing something, you couldn't install the software, so it was obstructive. Then we have some of them that had a forced action. So it wasn't enough to simply watch. You actually had to click on something or type something or do something before you could click install. And then we had our three composite tractors. So that's what we were testing. We had a whole bunch of research questions. As you can imagine, with all these different conditions, there are many questions. But just to show you some of the high-level questions, we wanted to find out whether the attractors would actually help people notice the publisher names. We wanted to know which of the dialogues would result in the fewest installs in that suspicious condition. We were also interested not only in the suspicious condition, but were people in the suspicious condition unknowingly, in an uninformed way, installing. So it may be that we have people who saw that it was Microsoft with two eyes, but they knew it was a study and they wanted to see what would happen, and that's why they installed it. So we wanted to distinguish those people and really only count those who really fell for it, who didn't realize what was going on. We're also interested in what happens in the case of the benign scenario. So this is a case that, we don't want to stop people from drinking wine, right? We want people to be able to actually use their computer and do things with their computer if it's safe to do so. And so we want to make sure that our dialogues just don't stop everybody from doing everything. We also want to make sure that that when it's a benign situation, it doesn't take too much time in order to actually go ahead and install something. And then we were also interested in whether sort of the more heavy-handed we were with the design, whether we would get better results.
We begin by studying the Android permission system, and we realize that there are many useful and simple policies that actually the permission system cannot specify or enforce. So one of them is this kind of information flow properties. So we focus on those and design mechanisms that can actually enforce distributed information flow control on Android. And using this system, we can probably prevent privilege escalation and information leakage. So this form of proof is actually quite important because the failed proofs actually allowed us to identify flaws in our initial design. All the scenarios are very subtle and complicated. If we didn't do the proof, then we wouldn't have been able to find these scenarios in our design. So this is saying that a formal proof actually is very important.
A graphical representation of this. So here again, we're representing the participants' agreement with the question. The password strength meter was annoying. Red indicates agreeing, blue indicates disagreeing. So ideally, we would want to see more blue than red. And if we look at how participants answered in all the different conditions that we had, we see that if you look at the top half in all the visual, for all the conditions are different, only in their visual features, there wasn't that much difference. There's a lot more blue than there is red. When we get to the meters which had different scoring strategies, in particular when we get to the strict meters, we start to see quite a bit more red. And you see here in the 1/3 score meter, not only is there more red overall, but there's actually a lot more of the deepest red than there is in the next next most annoying condition. there were meters that we tested that were both strict and didn't have a visual component, and those really nobody loved. So what are the takeaways here? So meters definitely worked, right? They lead to longer passwords almost no matter what kind of meter you try. Stringent meters help against these kinds of offline attacks. Possibly other meters too do, but that didn't show up in our study, maybe because of the smaller sample size. A nice thing which we weren't sure about is that meters don't affect memorability. That is, even though they're forcing you to create or helping you create a stronger password, they don't make for passwords that are harder to remember. And there's a limit. You can't just have a super draconian meter and expect usable and hard to guess passwords. When the meter becomes too strong, it seems like the benefits you get tail off and may even backfire when the users get frustrated and stop paying attention. In terms of specific features, scoring stringency was important, and having a visual component was important. What wasn't important was what the color was, whether the meter was segmented or not. The size of the meter was unimportant, and the bunniness of the meter as well.
So we're getting this really cool data. I mean, we have 1.5 billion SMT queries, 5.6 million going to the SMT solvers. To the best of my knowledge, this is probably the second biggest use of SMT. I think Microsoft is probably the biggest, but we're pretty close. We're into the billions of constraints. So there's many things that we're not perfect on. We don't claim to find all exploitable bugs. This is where we differ from the traditional verification community. Traditionally, verification says they're sound, meaning that they only say a program is bug-free if it really is bug-free. So we've invented a new term. We've invented a term called actionable. We only want to tell you there's a security critical bug when there really is one. Because we know there's 99,000 bugs out there. What we want to know are which ones we should prioritize first. We also only make all our claims of exploitability versus safe with respect to a fixed input size. So for example, we can tell you for many programs that no input greater than 10, 15, 32 characters will exploit the program. So there's lots of work we could do there. The sort of guarantees we give are different than the traditional verification community. We can make better symbolic executors. We can look at additional safety properties. One of the things we want to look at is information flow, for example. So there's lots that isn't perfect that we have to work on. In fact, there's, I think, 7 different theses we've mapped out in this area. But we continue to work on it. And at a high level, there's 3 things we want to do. The first is we want to continue to formalize what it means to exploit a system. And by formalize, I mean come up with the right formalization that doesn't just characterize what it means to exploit a system, but is also efficient to check. There's many ways you can formalize a problem, and often it's coming up with the right formalization that allows you to make progress. The second thing that we work a lot on is binary program verification techniques. For example, we're starting to investigate modular symbolic execution. Currently, symbolic execution starts when a program starts and ends when you get as far into the program as you can get. We want to be able to jump into the middle of a program and be able to do symbolic execution. And finally, and probably most importantly, we want to work on real code. We're not satisfied to go find 10 running examples that we can now check. We want to look at 500. We want to look at all of Unix if we can. And so we have this goal of getting 100% code coverage. And I just want to leave you with this final thought. We've checked 47% of code. We've come up with test cases for 47% of the lines of code on average. It seems wrong not to at least get to 100%. In fact, my personal belief is if we ever want to have hope in verifying 100% of the code, we at least have to come up with a test case for 100% of the code.